Hey, what's up guys? It's Nicola from Calcunic, and today we're going to be talking about proof by contradiction. Let's get right into it. Today we're going to be talking about the proof by contradiction. Let's start off by looking at the proof method. The first step in the proof by contradiction is to take the negation of the statement you're trying to prove and to assume that it's true. The next step is to show that the negation of the statement is impossible, or to show a contradiction. And by doing this, we have proof that the initial statement is true. You could think of the logic this way. If you have a statement and you know that the negation or the opposite of it is false, that must mean that the statement itself is true. Let's look at a simple example to solidify our understanding. Let's say we want to show that the statement that some cars are not Toyotas is true. Obviously, this is a true statement, but let's try to prove it using contradiction. The negation of the statement is that all cars are Toyotas. However, I can make the observation that my dad drives a Hyundai, and therefore, by showing a counterexample, I've shown that the negation is false, and therefore the initial statement must be true. Let's now try to apply our new knowledge on some more complicated examples. Now, let's try to prove that the equation 4x plus 2y equals 1 has no integer solutions. The general format for solving these questions is to first write, for the sake of contradiction, assume the negation is true. We have that the negation of the statement is that 4x plus 2y equals 1 has integer solutions. So we'll start there. We have 4x plus 2y is equal to 1. Now what we're going to do is divide both sides by 2. We have 2x plus y is equal to 1/2. And look at what we have here. We have 2x, and where x is an integer, so 2x is also an integer, we have y, which is an integer, equal to 1/2, which is not an integer. It's a rational number. We know that the sum of two integers can never be a decimal number. So therefore, this is a contradiction. Since the sum of two integers cannot be a decimal number, this equation is impossible, and therefore the negation is false. Concluding our proof by contradiction. We can now write a general final statement. As the negation is false, the initial statement is true by proof by contradiction. And there you have a general format for the proof by contradiction. Let's try another example. We are asked to show that m squared minus n squared equals 6 has no solutions for positive integers. And recall that 0 is not a positive integer, so we are only looking at numbers 1, 2, 3, and so on. Once again, we start by asserting that we are using the proof by contradiction. In this case, the negation of the statement we're trying to prove is that m squared minus n squared equals 6 has solutions for positive integers. Let's start with the given equation. We have m squared minus n squared equals 6. Now notice that we have the difference of two squares is equal to 6, and 6 is an even number. So either m and n are both odd or they're both even. Now because we've assumed that m and n are positive integers, we can separate them by using the difference of squares formula. So we write that m squared minus n squared is equal to m minus n times nm plus n equal to 6. Now if we look at what we had before, we know that either m and n are both odd or they're both even. We can recall that the difference of two numbers with the same parity is always even, and the same goes for their sum. And so therefore, both m minus n and m plus n are even. We could further note that the product of two even numbers is always divisible by 4. So therefore, m minus n times m plus n is divisible by 4. However, notice that m minus n times m plus n is equal to 6, but 4 does not divide 6. So this is a contradiction, showing that the negation of the initial statement was false, and therefore the initial statement is true. Now, this is probably the most common example people use when explaining the proof by contradiction. We're asked to prove that the square root of 2 is irrational. And a quick reminder for those of you that have forgotten, irrationals are just numbers that can't be expressed in the form of fraction, where both the numerator and denominator are integers. So if we're going to prove this using contradiction, first we have to assume the negation is true. So the negation for this is that the square root of 2 is rational, and we know a rational number can be expressed by a fraction. So we'll write just that. We'll say that the square root of 2 is equal to a over b And we have a restriction that a and b are integers, and this fraction is irreducible. So we can't reduce it anymore. A and b share no common factors. They are coprime. And so what we're going to do is we're going to rearrange this equation by multiplying both sides by b. So we'll have on the left side a is equal to b times the square root of 2. Now we're going to square both sides. So on the left hand side we'll have a squared is equal to b squared, and the square root of 2 is 2, so times 2. Now notice that a squared is equal to b squared times 2, and b squared times 2 is an even number, so we make the observation that a must be even. Now since a is even, we could write that a is equal to 2k, where k is an integer. Now we're going to replace the a in the equation above by 2k. So instead of having a squared is 2b squared, we'll have 2k squared is equal to 2 times b squared. If we expand this, we'll get that 4k squared is equal to 2b squared, and by dividing by 2 we get 2k squared is equal to b squared. Similarly to before, we make the observation, since 2 times an integer is equal to b squared, b must be even. So as before, we're going to say that b is equal to 2 times m, where m is just some integer. Now let's plug this back into the equation that we started with. We have root 2 is equal to a over b, which is, now we know a is 2k and b is 2m. However, notice that we have a common factor of 2, so we could cancel that out, and we have k over m. But wait a second. In our initial statement, we said that root 2 is equal to a over b, where a and b are two numbers that cannot be further reduced. And we just showed that they both contain a factor of 2, and so therefore can be reduced. This is a contradiction, and therefore we could conclude that root 2 is in fact irrational by the proof by contradiction. Alright guys, thank you so much for watching. If you had any questions or comments or other video suggestions, leave them down in the comments below and I'll try to get to them. If you like what you saw, if you feel like you learned something or just thought it was pretty cool, consider leaving a like and a subscribe. It's not much, but it really helps me grow my channel. That's all from me. Till next time.